Okay, YouTube, this is my second video in my module on exponents in which we're going to lay out all of the properties of exponents that we want to be familiar with. In the last video, we had explored the product and quotient properties of exponents. So we're going to start with those, but then we're going to move on to the other ones here, and then we'll put a few to use down here in these three examples. So starting with the product property and quotient property recaps, essentially we said, if a to the m is really saying we're taking a times itself m times, and we're taking a times itself n times with a to the n, if you basically multiply two things with the same basis, then the base stays the same. So we say same base, same base. We're really just saying how many total factors we had of a. So if we had m here and we had n here, then we have total m plus n here. So really, what this is coming down to saying is this: when you multiply two things with the same basis, you can just add their exponents. And likewise, when we talk about a quotient property, we're saying we have m factors of a on top and n factors of a on bottom. And so n of these on bottom cancel out with n of them on top, leaving behind the top exponent minus the bottom exponent's worth of exponent. So essentially, when you multiply two things with the same basis, you add their exponents. If you were to divide two things with the same basis, you subtract their exponents. And it's very important to list here that it is the top exponent minus the bottom exponent. This is very important that we always go in this order. Okay. So now, on to a very, very important property of exponents. That would be the power to a power property. And you can always identify a power to a power because you've got something that's being raised to a power, in this case a to the m, which in turn is also being raised to another power, n. And so when you raise a power to a power, you still get the same base here, a, but you multiply the two exponents. And so a perfect example of this, we could just kind of maybe list one here. We'd say 3 squared to the third. This would be the same thing as 3 squared times itself 3 times. 3 squared times 3 squared times 3 squared, which you can see is really just an extension of the product property, because I'm now taking 2 factors of 3 times 2 factors of 3 times 2 factors of 3. Really, when you multiply things with the same basis, you get the same base, but you add their exponents. So I get 2 plus 2 plus 2, which is 6. We could really have just said, hey, 2 times 3 here, that's how many factors of this base 3 that I have. Okay. So the power of a product property, okay, the interesting thing is the power of a product property is just an extension of the power to a power property. I want to point this out. This a in here is being taken to the first, and the b is being taken to the first by default. Anything that doesn't have an exponent listed has 1 for an exponent. And so really what we're doing is saying if we had an entire product that's being raised to a power, we can kind of distribute the exponent and multiply it by everybody's exponents on the inside. So ab to the m is the same as a to the m times b to the m. So a few things I want to list about this. First of all, it would mean something like this. If I had like x squared times y cubed, and I was taking this all to the fourth, this is a product to a power, okay, which means this: I can actually just go ahead and take this exponent that I'm raising everybody to and multiply by everybody's exponents on the inside. So x to the 2 to the fourth is the same thing as x to the 8th, because I can multiply their exponents. And y to the third, that to the fourth, is the same thing as y to the 3 times 4. I get y to the 12 without having to write all this out. And the second thing I want to list is this: if I had given you x squared plus y to the third all to the fourth, this is called the power of a product property for a reason, because it works with products. This is not a product. This one here is a sum. This is not okay to do. You cannot distribute this exponent through. This is bad. Okay, you can't do that if it's a sum or a difference. It only works if it's a product or a quotient, as a matter of fact. So we're going to skip down here to the power of a quotient property, and it essentially says this: look, if you ever take a fraction to an entire power m, you are allowed to multiply this one's exponent through to these one's exponents. And so you say a over b to the m is the same thing as a to that m over b to that m. So this would be something like, hey, 2 over x cubed to the, say, the 4th power. So this 2 here technically has a 1 on it, but we can go ahead and multiply this 4 through on its exponent. We end up with this. We say 2 to the 1 times 4 is 2 to the 4th. And then down on the bottom we'd say x to the 3rd, that to the 4th. And we know raising a power to a power, you multiply the exponents. We say x to the 3rd to the 4th is the same thing as x to the 3 times 4 is x to the 12. Okay. So now we have left ourselves down to the 2 most unique properties on the planet, but we're going to start with the zero product property here. And essentially the zero product property essentially states that as long as the base is not 0 itself, you cannot raise 0 to a 0. We say this is indeterminate. Not that you need to know this vocabulary term necessarily. Indeterminate. Okay, indeterminate form. But as long as the base is not 0, when you raise something to the 0 power, you get 1. Okay, and people often ask me to explain why this happens. Well, if you had 2 cubed, that'd be 2 times 2 times 2 is 8. 2 squared, for example, would be 4. If I had 2 to the first, I would get 2. What if I took 2 to the 0? And what you see is this pattern here that every time my exponent's decreasing by 1, I'm taking this and dividing the base out. I'm dividing by 2, dividing by 2. If I were to do this again, divide by 2 again, then the pattern would distinctly hold that I have a 1 here. Okay. Furthermore, actually, we could keep this pattern running. We know that anything to the 0 power is 1. What if I had 2 to the negative 1, which is something we're going to confront now with negative exponent. The negative exponent property, you can call it the reciprocal property, essentially, reciprocal. And this throws people at first, but let's say I continue this pattern. I divide this by 2 again. What I actually end up with is a half. Or if I had 2 to the negative 2, that would mean I'm continuing this pattern again, divide by 2. I'd get 1 over 4, or fourth. Or 2 to the negative third, I would get 1 over 8. Okay, so what I want to point out is this. Essentially, when I did 2 to the negative 1, I got the same thing I got when I took 2 to the 1. You can see that this pattern, they say there's some level of symmetry about these values here. 2 to the negative 2 is the same as 2 to the positive 2, or 2 to the negative 3 is the same thing as 2 to the positive 3. It's just that they're reciprocals of one another. So a couple things I want to say about this. First thing is this. When you take 2 to the negative 1, you're going to get the same thing as 2 to the positive 1, but it is the reciprocal of that thing. So essentially, when you have a base and it crosses over this bar on a fraction, this bar is called the vinculum. Okay, the vinculum. We say there's a fine line between the numerator and the denominator, and that's just a dumb joke. But essentially, anything that crosses over this vinculum, its exponent switches its sign. So in general, we could say this. If I had like a squared b to the negative 3 over c to the negative 4, this would be the same thing as a squared on top. It had a positive exponent. I have no problem with this. But since these have negative exponents here and here, we're going to take their bases and we're going to switch them around. It's not that I'm switching them around as much as I'm taking the c, I'm going to put it upstairs now, and if I put it upstairs, it becomes c to the positive 4. And if I take this base b that has a negative exponent and we switch it to being downstairs, it now has a positive 3. We've essentially reciprocated them. And these would mean the same thing. So again, if somebody says, hey, what's 2 to the negative 5th? Well, I don't know. What's 2 to the 5th? It's 32. So instead of getting 32, we'll get the reciprocal. We get 1 over 32. And this came out to being the same thing as, now keep in mind what I just said, if we were to take this base and put it downstairs, it would be down here now, and its exponent would become positive. And that would leave nothing but 1 on top. But that's the same thing as 1 over 32. Okay. So the 0 product property says anything to the 0 power is 1. Negative exponent property says, look, if you have a to the negative m, that's the same thing as the reciprocal of a to the m. Okay, as long as a is not 0. So we're going to use these properties down here. We're going to simplify these 3 expressions, and I want to list what the properties were that we used. Okay, so on letter A here we say we have 2 to the third to the fourth, and I notice that I'm not multiplying two things with the same bases. I'm not dividing things with the same bases, so this is neither a product nor quotient property. Not raising anything to 0. Don't have any negative exponents. Let's just come out and say it. This is a power being taken to another power. And so when you take a power to a power, recall power to a power says a to the m to the n is just the product of the two exponents. So we're still going to get 2, but we'll get 2 to the 3 times 4, which in this case becomes 2 to the 12th. 2 to the 12th. Cool. So that one was simplified. As a matter of fact, we can put this into a calculator and get a value, but I'm going to leave that for now as 2 to the 12th. Letter B, you notice that we have a quotient here. We're raising this quotient to a power. Okay, so quotient to a power property said this, look, if you're taking a fraction to the power of 2, it's really the same thing as taking everything on top, which was 3 to the power of 2, over everything on bottom, which is 4 to the power of 2. So we get 3 squared over 4 squared. And because I know these, we can actually simplify. We get 9/16. Okay, very quick way to do this. And then there was letter C. There is letter C. Important thing about letter C to notice is this. First of all, that the bases of these are the same. We are multiplying two things that have the same basis. So when you multiply two things with the same basis, we get to add their exponents. Really, I'm asking how many factors of -5 do we have total? A couple other things I want to mention. The base of this exponent on each of these is -5. I know this because I put them in parentheses, so I am including the negative, with these bases. And then last but not least, we have a negative exponent here. So let's start with this. If I'm multiplying two things with the same basis, let's go ahead and say, well, I still get the same base. I want to know how many total factors of negative 5 do we have. So we're going to add the exponents. Negative 6 plus a positive 4. So we say negative 6 plus 4 is my exponent. So I get negative 5 to the negative 2. Okay? And so since this is a negative exponent, we could put this over 1. That would be the same thing as reciprocating this. In other words, we're going to take this base and we're going to switch it over this vinculum bar to make its exponent positive again. So that's going to leave nothing but 1 on top. But our negative 5 comes downstairs. It doesn't become positive, but its exponent does switch its sign. Okay, so this becomes a positive 2. And to simplify this one step further, we could say, well, now I can square my negative 5. I get this 1 over negative 5 times negative 5, which is 25. So using these properties of exponents, we can simplify a lot of base exponent type of expressions. In the next video, we'll talk about simplifying even more complex ones. Cheers.